Hello. This example is going to show you a suggested methodology that you should follow when doing your Verilog design labs. In the early labs, you'll be given a complete design via a schematic and then be asked to implement it in Verilog. In later labs, I'll just give you a set of specifications and you will be expected to come up with the design. This example design right here takes the maximum of 3 numbers. The numbers are in single precision floating point format. I have A, B, and C. We're using the floating point single compare module that you're going to do in lab 2. This module compares 2 single precision floating point numbers and has a signal called A less than B that will be true if A is less than B. We use 2 of these modules in this design to get the maximum of A, B, and C. So how does this work? This portion of the data path right here compares A and B and passes the maximum of A and B to this signal right here. So in looking at this, how this works, if A is less than B, then I want to pass B through this 2-to-1 mux as the maximum. Else, if A is not less than B, then I want to pass A through here. This portion right here works exactly the same as this portion up here, except it's comparing max AB against C. So this signal right here, A less than B, if A is less than B, if max AB is less than input C, then I want to pass C as the maximum value to my final output. Conversely, if A less than B is false, that is if max is AB is not less than A, not less than this B input, which is C, then I want to pass this as the maximum value. In the end, the Y output will be the maximum of A, B, and C. So the first step is going to be we want to implement a Verilog module that implements our schematic. So I think I've done that. Back here in Xilinx, I created a project, added a Verilog file to it called max3 SPFP for single precision floating point. I have 3 inputs, A, B, C, and output called Y. I've instantiated one of these single precision compare modules. I've called it U1. That's going to be this guy right there. So I've connected A input bus A to A, input bus B to B. A less than B output signal, I've called it a name U1 underscore A less than B, declared it here, and I've connected it here. So that's this signal there. For the mux, what I've done is I've used an assignment statement to implement the mux. For this logic down here, I've done something similar. I've instantiated this. I've called that U2. So here's U2, and I've also made a mux to select between these 2 guys here. So I think I got it. I'm going to keep my fingers crossed, and I'm going to hope it works. So to compile this file, what I'm going to do is I'm going to select it here in the implementation tab, and I'm going to go ahead and say implement top module, and it's going to try and compile this guy. If I have any syntax errors, those should show up fairly quickly. Right now it's working on it. It looks like it's found some errors. It says process synthesize failed. If I go to my errors, it will tell me where my errors are. It says I have a syntax error at line 35. If I click on this, it says I have a syntax error right here at line 35. I don't really see anything wrong there, but actually the syntax error, it just says it's near this line. The syntax error is right here. I'm missing a semicolon right there. So let's go ahead and add that. I'll save it off, and now I'll rerun the process. I'm going to go ahead and do implement top module and see what happens. Some things get a spin over here. I'm going to get a lot of output here as it's working. Syntax errors are really easy to find. It'll point you at the where the error occurs near the line, and you just have to take care of them. Once it finishes, I get some errors down here that says process map fail. If I click on errors, it says the design is empty, no processing was done. What does that mean? I need to look at the design summary, And look at the parser errors. That's parsing the Verilog to see if there's any syntax error. There's no errors there. So now let's look at something called synthesis messages. There's some things in here that have warnings, and if I look at a couple of them, it says all outputs of instance U1 of block FPSP compare are unconnected. Underlying logic will be removed. What does that mean? It's saying that for some reason the outputs of instance U1 are unconnected. It also says the outputs of U2 are unconnected. And in fact, it says it's all these messages telling me that all of my logic is what the logic is unconnected. What does that mean? This is called a synthesis error, and what it means is that you've written some syntactically correct Verilog, but the logic that it's producing is incorrect logic, and it's because of a mistake that I've made in writing the Verilog. And these can be hard to find until you get more experience with Verilog. If in the design, the synthesis tool starts telling you that it has unconnected or loadless signals and that it's throwing away logic, then it means that your output ports are not connected for some reason. So let's go back and take a look at this Verilog and look at it more carefully. So a synthesis error is where it's trying to actually map this Verilog to gates, and it just told me that it's thrown away all my logic, and I said that it could be because my output is not driven. So let's go ahead and trace backwards and see where my output is connected. So here's my Y output. It should be connected to this MUX right here. So let's go to my Verilog and let's take a look and see where Y is. So I'm gonna do a look for Y. This is my output. Here's my MUX, and I've called the output of my MUX max. I did not call it Y. Well, that's the problem. For some reason I was writing this Verilog, got careless, and I just called this a different signal name than what my output actually was. So what I need to do is I need to go ahead and make this be Y. That's what it should be. Y should be assigned to the output of this MUX. Now I had put that error in there intentionally in order to generate this, but this is the kind of errors that you're going to run up against. Just because you have no syntax error doesn't mean that your Verilog is correct. So at this point, now that I've fixed that, let's go ahead and rerun implement top module and see what happens. So it finished, and it said at the end, it says process generate post place and route static timing completed successfully. That means it's mapped the design all the way down to the FPGA successfully. I can look at the design summary page here, and now if I take a look at some of these messages, there's still some errors. There's still some warnings here. Let's see what this is. So let's go back to the design summary. It says output port A equal B of instance U1 is unconnected. Well, actually that's true. This design has another output port that I'm not showing you called A equal B, but I don't need that in this design, and it's unconnected. And so I don't care that I'm not using that. And this is the same thing here in terms of on this instance right here, that output port A equal B is unconnected, and that's fine. Now that we've successfully placed and routed our design to the FPGA, one thing that I'll always ask you in a lab is, how many lookup tables did this thing take? What that means is is a measure of how much combinational logic is in this design, and it's going to add, and what I'll be looking for is a number of slice LUTs, which stands for lookup tables. Here I've used 89, which is only 1% of this device. Later on, when we use flip-flops, there'll be flip-flops appearing in here as well. But for right now, since we're just doing combinational logic, the only thing that will show up in here will be lookup tables. So let's go ahead and simulate this design. I'm going to go click on the simulation tab. I have this test bench that I'll always give you a test bench. And here's a test bench. We'll talk about this guy in a moment. But this guy is going to apply test vectors to the design and then check to see if your design works. So I've clicked on the simulation. I'm now going to go ahead and say, let's simulate the behavioral model. So let's do that. So I'm going to say run, and let's see what happens. Hopefully my vectors will pass. So it's popping up here. Let's take a look. Oops. I have some fail messages here. I have a couple of, here's a pass here, here's a pass there. So somehow I have something wrong in my design. I'm not passing all of these vectors. This is going to happen. You don't have any syntax errors, you don't have any parser errors, any synthesis errors, and yet your design is still not working. It's because you've made a mistake in writing the Verilog. So how are you going to debug this? So let's go back to Xilinx for a second. Notice that here, when I look in this, I have a choice of several different simulations I want to run. The first simulation you always want to run is behavior. That's where you want to debug your design. That means that you're simulating the Verilog without it actually mapping to gates. The reason you want to do that is because you're going to be able to actually look at internal variables in your design, internal signals in your design, and see what values they are. So in order to debug your Verilog, you're going to have some understanding of what this test bench does in terms of applying vectors to your design. You don't have to have a deep understanding, but you do have to have some level of understanding. So let's go over it. All of the test benches that I supply, at least initially, are going to look about the same. It's going to instantiate the unit under test that you're trying to test. In this case, this module called Max3 SPFP for maximum of 3 single precision floating point numbers. Here's my ports A, B, C, and Y. Then it's going to have a process that's going to initialize the signals. It's going to open a test vector file, and it's going to go into a loop here in which it reads each line of the test vector file one at a time, and each line will contain a test vector. It'll apply those values that it reads to the signals, and then it will delay for some time period. This #100 says delay for 100 nanoseconds while these changes propagate through the circuit, and then it will check the result, the output value here, and see if is it equal to the expected. If it's equal to the expected, then it'll print a pass message. If it's not equal to the expected, it'll print a fail message. Well, what is in this vector file? Let's take a look at that. So in this case, this vector file has these 4 hexadecimal numbers, and that's the only thing that the file is going to read from this line. Here I'm reading 4 hexadecimal numbers. The rest of this stuff it just ignores. So what are these 4 numbers? These are actually single precision numbers in hex format. This comment out here tells you what the decimal floating point number is. So this guy right here is this floating point number for A. This guy is this one for B, and so forth. What is this 4th value? This 4th value is the expected result. So the maximum of A, B, and C here should be this value right here. Why is that here? It's because this is a negative. These are all negative, and so the number that's going to be the maximum is going to be the one closest to 0, and it turns out this guy right here is the one that's closest to 0, so that's the maximum. So that's one line of the test vector file. So once you understand how test vectors are being applied, the next thing you got to do is make sense of what you see out here. So let's take a look at this. In this guy right here, I'm looking at this is going to be the hierarchy of my design, and this is showing me the signals and variables that are in my test bench, and that's what's actually being displayed here. So if I see Y, A, B, C, A line, file descriptor, count, status, whatever, that is actually all the stuff that's the variables that are in my test bench. And to be honest, that's kind of useless. What you really want to see is the signals that are actually in your design. So we would like to see the signals that are in here. We want to see A, B, C, but we also want to see these internal signals. We want to see that guy right there. We want to see this internal max A, B. We want to see these signals right here. So what am I going to do? Well, the first thing, here's what I always do when I start the simulation. First thing I'm going to do is I'm going to select all these signals here, and I'm going to delete them because I don't want them in my waveform. That's not what I want. I'm going to click on my UUT here, and I'm going to just select them all, and I'm going to add them to the waveform window. The next thing that I'm going to do is I'm going to change all this stuff to hex because binary doesn't do much for me. So I'm going to change all of these guys to hex. So I'll select all the signals, do a right click, go to radix, and go ahead and put them as hexadecimal numbers. Finally, so I don't have to do this over and over again, what I'm going to do is I'm going to do File, save save as. I'm going to save this configuration file, and I typically name it the same thing as whatever my design is, and this is going to be max3 sp fp dot, and I'll just let it go ahead and write it as a configuration file. If I go ahead and do save as again, you can see that it's out there. So that's a waveform configuration file. I'm not done yet. I'm not going to override it. I've already saved it out there. I'm not done yet. I'm going to go ahead and close this guy down because I'm going to restart it later. And so that I don't have to actually do this each time, what I'm going to do is I'm going to click on this, and then I'm going to do process properties. And in this process properties, I'm going to say use custom waveform file. I'm going to select this. So I'm going to select this guy, what I just saved, and say OK. And now every time I run my behavioral model, I'm going to have what I just did. So let's do that. So I'm going to do run. And it's going to pop up. And now I have just these signals appearing, and they're all in hex. And this stuff is now actually going to become more readable. So at this point, we can actually start doing some debugging. So how do you debug hardware? Well, the nice thing about debugging Verilog and hardware is that you have complete observability. I can see every signal at every instant of time. It's not like debugging a program where you single step through a program and you stop it, look at some variables and so forth. Here, I've simulated the design, and at each instant of time, I can see what each individual signal is. So what I need to do is locate where I am failing. So let's go here, and I'm actually failing on the very first vector. By the way, this number right here is the line of the file. This number right here is the time, and it's the time in, I think it's in picoseconds, and this guy right here is in nanoseconds. So I need to take a look at, where am I applying my vectors. So here, my A input, here's this BC, that's the A input, so that's A. This B, so this guy right there, if I move this yellow line over, this is my first vector. And so here, so I've applied A, B, C, and I get an output, but it's the wrong output. It's choosing the wrong value. What value should it be choosing? Well, let's go back and take a look. I can't tell much from this hex, so I have to go back and take a look here, and let's see which one of these guys is choosing. It's choosing this BC guy here, which BC is actually A. So let's just walk through our design and see what it should be. We said that the maximum value should be this guy right here, which is actually B. So our very first comparison, where we compare A against B, for the maximum value, we should choose this. So how can I tell if that choice is being done correctly? If I go back to my schematic, and so let's take a look at that. When I compare A against B, the result is going to go out on this bus right here called max AB. So let's see what the value of that max AB is. It should be the value of this B, which will be whatever this 9E, whatever is. So let's take a look at max AB. Here's max AB. It should be, what I say, it should be this 9E, which is going to be B correspond to that, but instead max AB is BC. It's actually A. So we're screwing up right here in this very first comparison. So why is that wrong? Let's go take a look at our Verilog, and let's compare what we wrote in this MUX versus what's in our schematic. So in our schematic, what we said was, okay, if A is less than B, we want to choose this B input. So if this is true, we want to steer B to this output. So let's see what we wrote in our Verilog. So look in our Verilog, if this is true, we want to steer, oops, there's the problem. Instead of steering B here, we're steering A. So I have these two things reversed. So let's go ahead and correct that. So I'm going to go ahead and say B there, go ahead and do A there, and now I've done it, so I can save this. Now, because I've made such a minor change, I don't really have to implement the top module. I can just simulate this guy behaviorally. The reason that when I told you at the beginning to implement the top module before we start simulating is because I wanted you to go ahead and flush out any synthesis errors, because you might get synthesis errors are such that it might simulate behaviorally correctly, but then you still have synthesis errors. So I wanted to flush those out first. So I'm not going to go ahead and rerun this. I'm just going to go ahead and simulate the behavioral model. So in order to do that, I first need to shut this down and rerun it. So let's go ahead and do that. So I'll run. By the way, if you try and run it while the simulator is still up, you'll get an error message. So it's running. Now it says pass here, and it actually says pass down to here. Have I run on my vectors? Well, actually I haven't. I've run 9 vectors. In this file there's like 25 lines, and so I need to run it for a little bit longer. If I run it for 10 microseconds, it turns out that's long enough. And it turns out that, hey, I see this message, all vectors passed, and that's coming from my test bench here. If I take a look at my test bench, it looks at the error count. I'm checking each individual vector. If it's 0, then I've passed all the vectors. So it turns out I only had one mistake in my design, and that was this. And by looking at what it is that I expected, and then looking at what was going on in the simulation, I could debug it. What you cannot do is you cannot just blindly say, well, what I'm going to do is I'm going to go back and carefully check the schematic and try to just see did I faithfully translate this to Verilog. That, for a large schematic, that can be a long time. What you need to do is use some intelligent debugging, see what it is that's going wrong by understanding the test vectors, and then that will pinpoint in the Verilog where you need to look. Now that we've verified that our behavior simulation works, we need to go ahead and re-implement the design. So we'll go back to implementation. We'll implement our top module. It will re-implement this. The reason that we're doing this is that now we want to simulate the actual the place and routed gate level model. Typically, that will always pass. If your behavior model worked, and your gate level model should work. If it doesn't, it means that you have some fairly obscure logic error in your Verilog that can be difficult to find. And one thing that could cause that would perhaps be the presence of latches. There are some other reasons for that, and if you run across your physical gate level simulation not working, then you might want to come talk to me about what's going on, because those kind of problems can be difficult to find. So once this guy is finished, we're going to go back to our simulation tab, and we're going to run our behavioral model. So it's still running here. Should finish here in just a second. By the way, this place and route means that it's actually mapping it to the FPGA, and not only assigning things to lookup tables, but it's also determining the routing between those lookup tables on the FPGA substrate. All right, this time we're done. So we can go ahead and go to simulation. At this point, we want to go ahead and choose post-route simulation. And we'll run that simulation. We'll select our test bench, click here, and we'll run. Now, what you're going to notice is that when you're running the post, place, and route model, you're not going to be able to see the internal signals. You'll only be able to see the external signals of a module, and that makes it very difficult to debug problems at this level. So that's why I would tell you to come see me if you have problems with your post, place, and route model working. I very rarely see those not work. So here I'm not going to even bother changing these test vectors here, because we're not going to be able to see any of the internal signals in this UT. Here we see individual signals that have been mapped to the FPGA substrate, and they're not going to make too much sense to you at this point. So let's go ahead and take a look at this. It passed the first 9 vectors. Let's run the rest of them. Hey, they all passed, so congratulations. Your design is now efficiently done. You have passed both the behavioral and post-route simulations. So in summary, I've shown you a methodology for how to approach your Verilog labs. Please follow this methodology. It will make your life and my life much easier. One thing about I want to point out, when we talked about the synthesis errors that can occur, that whenever you do implement top module and you get some synthesis problems, take a look at a document that's on the class web notes. I give you a lot of different examples of synthesis problems. I just showed you one, unconnected output. There are others that you can have.